we're going to touch on something very near and dear to my heart as an astronomer, that is telescopes. Now, telescopes, your book talks about having the purpose of magnifying or zooming in on objects at a great distance. So being able to see something from afar. And that's indeed one of the early purposes of a telescope, and still a purpose used today, especially if you go bird hunting, right? If you have a pair of binoculars, you basically have a telescope for each eye, allowing you to zoom in on distant objects. You know, in ancient times, like spyglasses or eyeglasses were used to see if distant ships carried the pirate flag, or more likely the flag of an opposing country. If you look out from the distance and see a war frigate heading towards your merchant vessel and it's flying the colors of your mortal enemy, you probably want to turn around and head in the other direction. Galileo Galilei is often credited for the invention of the telescope, but that's not true. In fact, he wasn't even the only person to use it for astronomical purposes, the first person, but he was probably the most famous early person to turn the telescope to the heavens, and he made some amazing discoveries that really expanded our understanding of the universe and started chipping away at the geocentric or Earth-centered model of our solar system, moving it towards a sun-centered or heliocentric model. Now, the second purpose of a telescope for astronomers is to capture a lot of light in order to view faint objects. So if you think about it, your pupils, the little black part of your eye, they can get fully relaxed about 7 to 8 millimeters across. That's not a lot of area for light to get in. So very faint stars might not shine enough light into your eye for us to see them. But if you place a very large lens on a telescope or a very large mirror on a more modern reflecting telescope, you can focus all of that light down into the pupil or onto a camera film or a digital detector in order to see very faint objects. So the two purposes of a telescope are to view objects at a distance, to zoom in, and for bright objects that works great, looking at the moon, looking at Jupiter. But it's also used to capture light and look at very faint sources too faint for the human eye to see. Now the refracting telescope, it's a refracting telescope because it refracts, and that it uses lenses to bend the light. So again, image of a refracting telescope shown up here. A refracting telescope has two elements. It has an objective lens, which is the lens closest to the object. It's the larger of the two lenses, and then it has an eyepiece, which is placed at the same focal point as the objective lens. So in a telescope, a refracting telescope, the objective lens and the eyepiece share the focal point in the middle. That allows you to take a large amount of light from a distant object and focus it down to a smaller point, but also to allow you to magnify a distant object. So in astronomy, we talk about what's called the angular magnification. The angular magnification is the negative of the ratios of the two focal lengths of the lenses. So you take the focal length of the objective, again, the focal length of the large lens, divided by the focal length of the eyepiece, which is usually much, much smaller focal length, and that will give you the magnification of the telescope. The negative sign is there to remind you that the image is inverted in a simple refracting telescope. So if you have just a simple two-lens telescope that you make yourself, when you look through it, things will appear upside down. Now, when you're looking at stars, not a big deal. A star looks upside down, it still looks like a star. But when you're looking at, for instance, something in the distance, like a bird, having that upside down might be a little bit distracting. Reflecting telescopes, your book doesn't talk too much about that, but they are more modern telescopes. Larger university professional grade telescopes use mirrors instead of lenses. Lenses can only get so big. In fact, the largest refracting telescope in the world is actually in Wisconsin. It's called Yerkes Observatory near Williams Bay, Wisconsin, near Lake Geneva, but equidistant south of a line connecting Milwaukee and Madison. It's owned by the University of Chicago. Even though it's owned by Chicago, they built it in Wisconsin. It is a piece of glass 40 inches in diameter that weighs more than a ton, I believe. It took a year for that piece of glass to cool before they could shape it. Yerkes was made around 1895-ish, I believe was the date. So it's over 100 years old. You can't get lenses much larger than that because they tend to sag under their own weight. So about 40 inches, a little over a meter, is the biggest refracting telescope you can make. It's much easier to make a reflecting telescope. It's much easier to make a mirror and then give that mirror a slight curve in order to focus the light down. And most modern telescopes are comprised of either a very large single mirror up to 8 meters across, so much, much larger, 8 times the diameter of Yerkes. Or you can use individual smaller mirror segments very carefully aligned to make mirrors. I think the new design for the 30-meter telescope that they hope to construct in Hawaii, or start breaking ground in Hawaii over the next couple of years, is going to be 30 meters across. An incredibly large optical gathering instrument. And there are a lot of other advantages for reflecting versus refracting telescopes. Now, your book talks about adaptive optics. Adaptive optics can only be used on reflecting telescopes, and it's a fairly recent technology. We talked about how light bends when it enters material with a different index of refraction. And that index of refraction in air is very close to 1, but it's not exactly 1. And it also varies slightly with the density of the air. So hot air, which is less dense, has a slightly different index of refraction than cool air, which is more dense. So as starlight from a distant star enters our atmosphere and comes down to our eyes, it travels through different layers of our atmosphere that have different temperatures and could be turbulent. You know, you have jet streams and wind and so on in the upper atmosphere. That causes stars to appear to twinkle. Now, very pretty for a night sky or a photograph or just staring out into space, but very problematic if you're an astronomer and you want a very precise measurement of a star's brightness. So, modern technology can actually send up artificial stars, which are basically lasers, into the upper atmosphere and see how the atmosphere changes the known property of what that artificial star should look like. So we can see what the atmosphere does to the light. And little tiny machines in the back of the reflecting telescope and back of the mirror warp the mirror very slightly to undo that distortion. So you can actually do real-time, computer-controlled distortion correction for very faint objects, for distant objects in the sky, using what are called adaptive optics. Now in the spy world, this is useful because a spy satellite looking down, the atmosphere also distorts your vision. So if you want to take a picture of a license plate from space, you can't do it unless you have a machine that can actually undo those changes in the changes caused by the index of refraction changes in the air between you and your object you're taking a photo of. In astronomy, we look up, not down, like spy satellites. So we're looking at stars using this pretty cool adaptive optics technology. Or if you want to get above the atmosphere completely, just put a telescope into space, like the Hubble Space Telescope or the upcoming James Webb Space Telescope, which is supposed to launch in 2018. Now, that's also very expensive to do. So while adaptive optics is incredibly expensive to do on the ground, you can repair it easily if it breaks. Space telescopes, you can't repair easily, right? In fact, it's almost impossible now to repair space telescopes with the discontinuation of the US shuttle program. So the Hubble Space Telescope is up there until it fails. And once it fails, it's done. So, brief overview of telescopes, and we're going to look now at what are called aberrations, or errors in viewing when you use these optical instruments.